compared to what I originally wrote. So take that as you will. But yeah, feel free to give me feedback on the nature of the problem sets, how difficult they are, especially like if there's some prerequisite that I'm assuming that you haven't seen, let me know, because that's the sort of thing that I don't always know. Okay. So for example, a lot of this first problem set that you guys are just finishing now I'm assigning it because last year when I taught this course, I discovered that people actually needed reminders of things like harmonic oscillators, summation notation, even for those of you who've seen it before, stuff like that. Okay. So do let me know if there are any prerequisites that, would you mind closing the door, actually? Thank you. The foosball is sort of distracting. If there are any prerequisites or something that you need to brush up on, because then I can give you another problem, which will help you brush up on that. Okay, well, today is very exciting. So today I'm going to continue our discussion of classical field theory. Oh, it's red. Okay. Sorry. Okay. Talk amongst yourselves for a second there. Pen, color, black. Okay. So today I'm going to continue with our discussion of classical field theory. Before, by the end of this class, moving on to the quantization of the theory of fields. And by the end of next Tuesday, let's say, we'll understand the simplest quantum field theory. Actually, the simplest quantum field theory is the one that you did on the problem set. So we'll understand a slightly less simple quantum field theory. Okay. And in fact, it's actually kind of the same quantum field theory. So just to remind you of where we left off last class, so we introduced a scalar field. And what is a scalar field? So we usually denote it phi. It's a function of points in space-time. And it's the basic dynamical object in both classical and quantum field theory. So what is it? You can think classically phi of x mu is an assignment of a real number for each point in space-time. So it's a number for each point in space-time. And if you want to think of a sort of simple dynamical model of a classical scalar field, you think of this model that I introduced last time of a bunch of balls on springs going on forever. And you think of, say, the vertical displacement of the ball from its equilibrium position as the value of the scalar field at the point x. So in the simple mechanical model, I'm really thinking of space as a lattice, one for each one of those lattice sites at which each of the balls lives. But you then imagine taking the limit where the lattice sites become very, very closely spaced, and then you can you can think of this as some sort of continuous field phi. So one real number per each point in space-time. Okay. Now, when I say a real scalar field, that means I'm talking about one real number per point in space-time. But there are other kinds of fields that we'll be discussing in this class. So for example, I could talk about a complex scalar field, which is a complex number per each point in space-time. The physics of complex scalar fields is very similar to the physics of real scalar fields, and the problem set I just handed out is essentially an exploration of the physics of complex scalar fields as a way for you to get used to dealing with some of these techniques. Another example of a field would be the electromagnetic field, which you can think of as a set of four quantities, a mu, the electromagnetic 4 vector, as a function of points in space-time. So that's an example of what we would call a vector field, because it's a 4 vector per each point in space-time. And then, so in this class, we'll mostly be thinking about scalar fields, vector fields, as well as spinor fields, which will describe particles that have fractional spin. And of course, in the world of quantum field theory, there are all sorts of other fields that people sometimes consider. For example, if you want to describe gravitation as a field theory, The theory of general relativity is a classical theory where the basic dynamical object is not a single scalar, a single real number per point in space-time, but a matrix of 10 real numbers known as the metric per point in space-time. And just as when we quantize this real scalar field, we'll find particles. If you were to quantize the other sorts of fields that you have, you would find particles associated with that. So for example, the quanta associated with the 4-vector A mu are known as photons. The quanta associated with the 4x4 symmetric matrix with 10 components, known as the metric, are known as gravitons, and so on and so forth. Now, so far we've just discussed the classical dynamics of scalar field. And the basic dynamical principle is that the equations of motion are found by minimizing an action and that action is the integral d4x of some Lagrangian. And here now it's not a Lagrangian that's integrated dt to give you an action as it would be in standard mechanics. It's a Lagrangian density that's integrated d4x. So this Lagrangian density is a function of points in space-time that depends on the field variables. And in particular, in the theories that we will be studying, it depends on the field variables and their first derivatives. Just like the Lagrangian in classical mechanics depends on the degree of freedom q and its first time derivative, q dot, the Lagrangian density in field theory will depend on the field phi, as well as the set of 4 first derivatives, d mu phi. And in order to determine the equations of motion, we minimize with respect to an infinitesimal variation of the field. So essentially we take the derivative of the action with respect to the field. More precisely, we would say the variational derivative with respect to the field of the action, and we set it equal to 0. And that implies the Euler-Lagrange equation, which we derived last time, where if we write it using Einstein summation notation, it takes the form that I've written here. And this is the generalization of the Euler-Lagrange principle in classical mechanics, where you have just a finite number of degrees of freedom, to a field theory where you have an infinite number of degrees of freedom, one per each point in space. And generally, if you're confused about quantum field theory or even classical field theory, it's very useful to just remind yourself to rephrase everything in terms of this lattice of points here and think about everything in terms of a large but finite number of classical degrees of freedom in the sense of, sort of standard classical mechanics. Are there any questions on that before I continue? So if you don't remember exactly the derivation of the Euler-Lagrange equation, don't worry. You'll get a chance to understand it in more detail and generalize it on the problem set that I just handed out. Okay. And I suppose you worked through it in detail when you just derived the equations of electromagnetism on the problem set that you're about to hand in. Good. So what I really want to do is begin discussing the quantization of these theories. But before I do, I want to take a little bit of a detour and talk about what I think is probably the single most important principle in physics, if you had to choose one, and how it applies to quantum field theory. And that principle is Noether's theorem. So have you guys all seen Noether's theorem in your mechanics classes? Okay. So just to remind you, Noether's theorem is the statement that whenever you have a physical system, if that physical system has a symmetry, then that implies that there is some sort of conserved quantity associated with that symmetry. Okay. And what I'd like to do now is work out the consequences of this in the context of classical field theory. So first, I'll need to tell you exactly what I mean by a symmetry. So a symmetry in field theory means exactly the same thing that it did in classical mechanics. In particular, it's a transformation of the basic degrees of freedom, which in this case are the field variables. So let's say you have some field phi of x. What you do is you describe some transformation where phi of x is rewritten in terms of a new field that I'll just call phi prime of x. So phi prime of x is going to be some function of phi of x. And the basic property is that it leaves the equations of motion unchanged. In particular, if you rewrote the equations of motion in terms of the field, the new field phi prime, they would take the exact same functional form as they would if you wrote it in terms of phi. Okay. And so we'll see several examples of these sorts of symmetries. So how can we exploit the presence of a symmetry in the context of field theory in order to derive some sort of conservation law? So the first thing that I want to notice is that instead of talking about the equations of motion, it's a little more easy to think about a symmetry in terms of the action instead of an equation of motion. So in particular, because the equations of motion are found by minimizing an action, if the action is left invariant under this change of field variables, then that implies that the equations of motion will be unchanged. Right? Because the equations of motion are found by varying the action with respect to the field variables. If the action is unchanged, then the equations of motion can't change. So if you look at this expression for the action that I've written down up here, then you can ask, how must the Lagrangian density change in order to leave the action unchanged? And if you stare at that for a second and you remember the fundamental theorem of calculus, you'll see that that means that under the symmetry transformation, where phi goes to phi prime, the Lagrangian density can only change by a total derivative. Right? Because the integral of a total derivative is equal to 0. Or, let me say that a little bit more carefully, the integral of a total derivative is just some sort of boundary term that's going to be independent of the value of the field sort of in the interior of space. Okay? And so all that the addition of a total derivative to Lagrangian will do is shift the action by an overall constant. And if you change the action by a constant, you're not going to change the equations of motion, because the equations of motion are the derivative of the action with respect to the field variables. They're the first variation of the action with respect to the field. Is that clear? Are there any questions on that? I mean, I'm going through this a little bit quickly because this is essentially identical to the manipulations that you've already seen in the context of classical mechanics. So the symmetries that I'm going to be interested in are not just any old symmetries, but what are referred to as continuous symmetries. So a continuous symmetry is a family of symmetries that depend on a continuous parameter that I'll call alpha. Maybe I'll call it epsilon. So that, for example, the change of field variables, so phi is a function of your point in space-time. And under this symmetry transformation, it'll go to some phi prime that depends on where you are in space-time, as well as our parameter epsilon. And I'll choose my parameter epsilon so that when epsilon equals 0, you don't do anything. Okay. So when epsilon is equal to 0, you just get phi of x again. And then you'll get something at linear order in epsilon that I'll call the first order variation of phi. plus terms that will not be important to me. So presumably, this is exactly what you did when you derived Noether's theorem in classical mechanics. You considered continuous symmetry transformations. An example of this, which is a good one to keep in mind for the purposes of today's class, is time translation. So if the equations of motion of your theory are invariant under time translation, as all of the equations of motion essentially that we'll be studying in this class are, then that means that you have a symmetry where you think of phi of xt being translated. So phi prime will be phi x and t plus epsilon. So here I'm translating an amount in time proportional to epsilon. And then if you take epsilon to be very small, you could Taylor expand and you just get phi of x and t plus epsilon phi dot plus higher order terms in that Taylor expansion. So in this case, the first order variation of the field is just phi dot. And, okay, let's see how much you remember the conserved quantity associated with time translation. Anybody? Please? Okay, thank you. The conserved quantity associated with this is going to be energy. Okay, so let's now imagine what happens when we have a continuous symmetry. So under a continuous symmetry, where phi goes to phi plus epsilon delta phi, let's ask how the Lagrangian transforms. So the Lagrangian will go to the Lagrangian plus delta Lagrangian. Okay. And remember, the Lagrangian is a function of the field and its first derivative. So if you do an infinitesimal transformation of the Lagrangian, then the chain rule of the field, then the chain rule tells you how the Lagrangian changes to first order. So the Lagrangian is a function of the field. So you'll get, epsilon dl by d phi times delta phi, and then dl by d mu phi times d mu delta phi. Okay. So both of which are proportional to epsilon. Oops. Okay. Good. There we go. And we can rewrite this, of course, as epsilon times the equations of motion plus a total derivative term. And what is that total derivative term? Well, it's d mu times dl by d mu phi times delta phi. Right, this is just the usual integration by parts that we use to derive the equations of motion. And remember that in order for the action to be invariant, the variation of the Lagrangian density has to be a total derivative. And so what I'll do, in fact, is I'll just take that total derivative to be proportional to epsilon. Okay, that's just a definition. Oops. Sorry, what am I writing here? Okay. Sorry about this. Someone should have told me that this equation makes no sense. The Lagrangian of the action is unchanged if the Lagrangian changes by a total derivative. Okay, which means that you have to be taking the total derivative of some quantity. Right? Is that clear to everyone? Right? If you change the Lagrangian by a total derivative, grad mu of q mu, then the action will be unchanged because the equations of motion will be unchanged, right? Because the action will change only by the integral of q dotted into the normal vector to whatever region you're integrating over. And so in order for the action to be unchanged, the Lagrangian had to change by a total derivative. So we could in fact just rewrite that total derivative as epsilon times q. So let's just call it, for a continuous symmetry, So this will be epsilon times some total derivative. And so if you compare these two equations, that means that you have a quantity that I'll call J mu that's equal to, what is it, dl by d mu phi times delta phi minus q mu, which has the property that d mu of J mu is equal to 0. So sorry if that was a little unclear. The basic point is that when you have a symmetry, you think about the variation of the Lagrangian with respect to that symmetry, and you get the equations of motion plus a total derivative term. And the Lagrangian, you know, in order for the action to be invariant, has to change by some other total derivative term that I called q. And then you know that the difference between those two total derivative terms has to be equal to 0. So that means that you have this quantity J that we call a conserved current that obeys the equation d mu J mu is equal to 0. So it's worth staring at that equation for a second. And thinking of, so I'm using here this very compact 4-vector notation where I'm using Einstein's summation and thinking of J as a 4-vector, so it has 4 components, a 0 component, as well as 3 spatial components. But it's worth unpacking that for a second and thinking about it in a sort of more familiar 3-component language. So let me call the 0 component the time component of that 4-vector J0. And the spatial components will be some vector that I'll call J. Then this conservation equation is the statement that J0 dot is equal to grad dot J. Okay. Or if I rewrite this in a language that might be more familiar, if you think about electromagnetism, then the sources that live on the right-hand side of Maxwell's equation are, well, either a current 4-vector, if you use the Lorentz invariant notation, or if you just write the standard Maxwell equations, they're a charge density rho along with a current density J. Then these equations that I've written down here, rho dot equals grad equals the divergence of J, are the usual continuity equations for any conserved quantity. It says that rho is some sort of local charge density, and J is a current, and the amount that rho is changing at some point in space-time is equal to the amount of current flowing out of that region. That's something that you probably saw in your electromagnetism class. Question?
Isn't there supposed to be a minus?
There's probably a minus sign. Well, let's see. There's a minus sign. Remember, yeah, I don't actually. Oh, yeah, there's a minus sign. Okay. Sorry, I'm not very good with minus signs. No, there's no. Yeah, there's no. There's probably a. Yeah, probably sure. Put a minus sign in. Yeah. What's that? Yeah, maybe there's like a minus sign that or something like that. I don't know. Okay. I'm not very good with minus signs. I do my best, so please bear with me. Yeah. So probably, okay, I don't think there's, actually, yeah. Okay, probably there's a minus sign. Yeah, I can never quite remember these things. Sorry. Maybe rho J is the thing where you have upper indices, not lower indices. I probably just gave you a problem set on this, didn't I?
Yeah, I think it was one.
Okay, fine. So you know better than I do where the minus signs go. Good. Okay, but is the basic idea clear? So in general, given a conserved current, J mu, what do you do with that current? Well, if I hand you a charge density rho, what do you do with that? Well, you integrate it over all of space to find the total amount of charge. Okay, right? That's what densities do for a living. They're things that you integrate to find numbers. So in particular, you can take J0, the 0 component of that. Let's give it a name. Let's call it Q. And then you could imagine taking the time derivative of that. So that's the integral d3x, J0 dot, which is the integral d3x grad dot j, and the integral of a total derivative is equal to 0. So that tells us that whenever you have a conserved quantity, you can take the 0 component of that 4 vector, integrate it over all space, and you get something that's unchanged in time. So if we were talking about currents, the current 4 vector, the thing that you get is the charge, like literally the electric charge. Okay? If we were talking about the current 4 vector that you get from time translations, then you would get some sort of density J0, which you would call the energy density, and you integrate that d3x and you get the total energy of the system. So let's go ahead and work out what that is, but before I do so, let me pause and see if there are any questions. Everything more or less clear? I know that sometimes these sort of manipulations can be a little tricky the first time you see them, but there's nothing too fancy going on here. So let's do an example. It's probably the most important example that we'll do. So let's imagine let's imagine time translation invariance to compute the conserved energy of some classical field theory. And in fact, well, we're all relativists here. So let's just not do time translation and spatial translation separately. Let's just do them all at once. So let's investigate a theory which has space-time translation symmetry, okay, as all the theories we'll study in this class will have. Okay. So in particular, you can imagine just moving either in the time direction or the space direction and getting either a conserved energy or a conserved momentum out of this. Okay. So under this change of variables, phi of x mu, we'll go to phi of x mu plus zeta mu, which one can just Taylor expand. That's phi of x mu plus zeta mu d by d x mu, phi of x mu plus higher order terms that we don't care about. And this is the variation delta phi. You know, I'm using zeta mu instead of epsilon here. If you like, you could think of zeta mu as some unit vector times the infinitesimal parameter epsilon that I wrote earlier. Now, how does the Lagrangian change under this translation? So the Lagrangian, of course, is also a function of x mu. So under a translation, it also just picks up this derivative term. So it's zeta mu d mu of L plus higher order terms. So that means that that thing that we called q mu earlier, in the present case, is zeta mu times the Lagrangian density.
Just a quick question.
Yes.
Is it really phi in the inline?
Sorry, it's not phi, it's L. Sorry about that. Good. Yeah. Please, I write down stupid things all the time. Let me know if I do so, and I'll tell you whether it was intentional or not. Good. Any questions? Any other stupid mistakes? Right. Okay. So what does that mean? That means that we have a current. What is that current? Well, we just take this expression and we plug it in to, where did I derive it? We plug it into this formula here. So we know what, and so we have a current. So J mu is dl by d del mu phi delta phi minus q mu. So here, mu is just a dummy index, and I don't want to confuse it with the mu index that I put on the zeta here. So I'm going to relabel it nu. Okay. So J nu, what was that? So that's dl by d nu phi delta phi minus q nu. I'm just rewriting the equation that I wrote down above. Now let's plug in these expressions that I derived up here. So we have dl by d nu phi times d mu phi times zeta mu minus zeta nu L. So that's the conserved current. In fact, we see here that we don't just have one conserved current, we have 4 conserved currents. Because zeta mu could take any one of 4 values. It could be a translation of the x, y, z, or t direction. So you actually have a set of 4 conserved currents. And so it's convenient to repackage these a little bit. So I'm going to write this as, so I'm going to first note that this quantity that I derived over here, it's linear in zeta. So I'm going to write that as zeta mu times t nu mu, where t nu mu is just the same thing that I wrote down above. So d mu phi, d mu phi. And here it's minus the Lagrangian density times delta nu mu, where delta nu mu is the Kronecker delta symbol. So delta nu mu is equal to 1 if nu equals to mu, and it's equal to 0 otherwise. It's a fancy name for the identity matrix if you thought about this as a 4x4 matrix. So t nu mu has a name. It's called, well, it's got 2 names actually. It's sometimes called the stress tensor, or it's sometimes called the energy momentum tensor. Sometimes called the stress energy tensor, but very rarely called the stress momentum tensor. Okay, see, that's a joke, you guys. It's too late in the day. And it obeys a conservation law. So d nu t nu mu is equal to 0. So you guys presumably have encountered the stress tensor before, possibly in your electromagnetism class. Did you see if you took a Griffiths thing, I know he has the stress tensor of electromagnetism, right? You probably don't really understand it. Okay, but so here, now you're getting a chance to understand it. Okay. So let's just unpack a little bit exactly what this guy is. So this is a 4x4 matrix, because mu and nu both take one of 4 values. And let's just think about its various components. So what is T00? Okay. So the first thing to notice is that because I'm raising and lowering indices with the metric in the t direction is just 1. So that's the same as T00. So I'm going to give a name to that quantity. I'm going to call it H. So what is it? Well, remember that this component down here, so if that's equal to 0, we're calculating the current associated with time translations. And if this thing is equal to 0, that's the thing that you integrate in order to get a conserved quantity. So the thing that you integrate in order to get the conserved quantity associated with time translations is the energy density, because the conserved quantity associated with time translations is energy. And so T00 is the energy density of your theory, also referred to as the Hamiltonian density. What is Ti0? Well, Ti0, if you remember your conservation law, so if you looked at this conservation law here, it plays the same role to energy density as current plays to charge density. So it describes the energy flux in the ith direction. So here I'm using the notation where I runs from 1 up to 3, so it doesn't run over 0. Similarly, T0I is going to be a momentum density. So it's a momentum, let's write it this way. It's the density of, let's call it I momentum density, or I momentum. So, you know, if you have x momentum, it's the density of x momentum, the thing that you integrate in order to get the total x momentum. And Tji is the flux of I momentum in the j direction. Something that we're not usually used to thinking about. It doesn't arise all that often in sort of very simple examples of mechanical systems, and it's sometimes known as shear. So this is an example of a set of conserved quantities that I've computed in terms of the Lagrangian for translations in time and space. In the problems that I just handed out, you'll compute the conserved quantities associated with you'll compute the conserved quantities associated with gauge transformations, which will lead you to conserved charges rather than conserved energies. But what I want to do is just explore a little bit further the form for the energy density H that I derived above. Okay, so what is that energy density? Okay, we can just plug it in here. We can just plug it into that formula. So that's dl by d phi dot times phi dot minus L. Okay, that's just plugging in our formula for the stress tensor. So, in fact, that formula might look a little familiar to you from your classes on classical mechanics. So just remember in classical mechanics, if you have a single degree of freedom Q and a Lagrangian L, so let's say this. So if you have some degree of freedom Q, and dynamics that follows from a Lagrangian L that depends on Q and Q dot, then we define the momentum conjugate to Q. So that's defined as the derivative of L with respect to Q dot. And the Hamiltonian of a system is defined to be P times Q dot minus the Lagrangian. And we regard that Hamiltonian not as a function of Q and Q dot, but as a function of Q and P. And then from that you could write down the Hamiltonian equations of motion, or if you're very brave, try and quantize the system. And H is the thing that will become the quantum Hamiltonian, and P and X will become the quantum mechanical operators that tell you about position and momentum. So this boxed equation for the energy density up here looks very, very similar to the equation for the Hamiltonian that I've written down here. And that's not an accident. In particular, if you remember how we derived our classical field theory by taking a bunch of sort of standard degrees of freedom, you know, one for each point in space-time, and then promoting them to some field phi that depended on where you are in space. If you think about it, you'll see that that really means that you know, you had these QIs which labeled the values of the field at different points in space-time. The momenta conjugate to that will give you should be promoted to some momentum density. So in particular, when we promote QI to a position of space, you should also promote the momentum to a position of space. So we can define pi to be the momentum density. And just as the usual momentum is defined as the derivative of the Lagrangian with respect to Q dot, the momentum density we would define as the derivative of the Lagrangian density with respect to the field variable. So this is going to be the momentum conjugate to phi. Time derivative, sorry, thank you. And then the Hamiltonian of the system, so in classical mechanics, should be promoted to a Hamiltonian density. And what is that? That's going to be pi times, just copying down this equation here, but replacing the momentum by the momentum density and q dot by the derivative of the field. That's pi times dl by, sorry, that's pi times phi dot minus L, the Lagrangian density, and the total Hamiltonian, so the total energy, or the total Hamiltonian, will be the integral of that d3x. So indeed, the expression that we derived up here for the energy density is nothing more or nothing less than the Hamiltonian of classical mechanics when you have 1 degree of freedom per point in space. Any questions on that? Hopefully that's more or less clear. Thoughts, questions, feelings? Good. All right. So that sort of completes everything that I wanted to say about classical field theory. We're now in a very good position to start discussing the quantum mechanics of this theory. In particular, you've got a set of variables and their conjugate momenta, and you've got a Hamiltonian. Okay? So now you don't need my help. You know what to do. You've got a set of x's and p's, and you've got a Hamiltonian. How do you quantize the system? So to quantize the system, what do you do? Well, when you quantize a system where you have a dynamical variable q and some conjugate momentum p, what do? Well, you promote those to operators. So often they're denoted q hat and p hat, which obey a fundamental commutation relation. So the commutation relation is that the commutator of p with q is equal to I h bar, right? Or just equal to I, because we're using units where h bar is equal to 1. And then the Hamiltonian, regarded as a function of q and p, then becomes some operator where you just replace the q's and p's by the operator's q's and p's. So that's the standard recipe for quantization. Okay. Easier said than done, however, because what you really need to understand is what Hilbert space do these operators act on. Okay. And that's what we're going to do now. In fact, we're going to do it by turning this quantum field theory that we've been studying into a very simple dynamical system that you guys will hopefully all recognize. Any questions before I continue? Is there a question over there? Maybe before I do that, okay, let me just go through this Hamiltonian density stuff for a very simple example, the example that we studied last class, which is that of a free scalar field. So a free scalar field is a field phi with a Lagrangian, which is 1/2 d mu phi minus m squared phi squared. So in order to determine the Hamiltonian, let's write that out a little bit more explicitly, so as we did last time. So what is that? That's 1/2 phi dot squared minus grad phi squared, so grad phi dotted with grad phi, minus m squared phi squared. So in this theory, we can derive the conjugate momentum. So what is pi? it's dl by d phi dot. And just you look at the expression for L, what is that? That's just phi dot. Okay. And what's the Hamiltonian? Well, the Hamiltonian was, the Hamiltonian density is pi phi dot minus L. And we're supposed to think of that as a function of phi and the conjugate momentum. So let me write it as a function of pi and phi, instead of as a function of phi and phi dot. So what is that? That's going to be pi squared plus grad phi squared plus m squared phi squared. So that's the Hamiltonian of a free scalar field of mass m. With a 1/2, thank you. With some 1/2s, yeah, 1/2. Where's the 1/2? There's 1/2. Good. Good. Okay. So it's worth staring at that expression for the Hamiltonian for a second and thinking about it in the context of our dynamical model of scalars, of a scalar field as a bunch of balls on springs. So remember, the dynamical variable in this case was just the vertical displacement of the particles from their equilibrium position. Okay. So what is that 1/2 pi squared? Well, that's just the contribution to the energy from the kinetic energy of this ball on a spring moving in the vertical direction. You know, it's p squared over 2m, the kinetic energy of a free particle. What is this term here? You should really think about that as a contribution to the potential energy coming from from gradients of phi. You know, if this guy here is displaced way up there compared to this guy, then there's a strong gradient in the field, and that means that this little spring here is going to be stretched, and you'll get a contribution to the potential energy coming from there. And what's that m squared phi squared? Well, again, that's just some sort of potential energy telling you that there's a restoring force that makes phi want to be equal to 0. So it makes everything want to not be displaced in the vertical direction. Good. Any questions from that? Okay. Okay, now things are going to get fun. So to quantize this theory, and for this class, and probably all of next class, and maybe even all of next week, we're just going to talk about the quantization of the free scalar field. What do we want to do? Well, we want to take our canonical degree of freedom, phi, and promote it to some operator that I'll call phi hat. In fact, I could call it phi hat, but usually I'm going to be lazy and just call it phi. In the same way that in quantum mechanics, you know, you usually just eventually drop the hats once you get used to the fact that x and p's are operators. And the question is, what is the Hilbert space? And what is the Hamiltonian on this Hilbert space? So the first thing that we have to do is we have to write down the canonical commutation relations that are going to be obeyed by our degree of freedom phi and the conjugate momentum pi. So remember, we're being motivated by a system with a finite number of degrees of freedom. So if we have a system with a finite number of degrees of freedom labeled by some index I, then the canonical commutation relations take that form. So let's say that I labels which of those little masses connected by springs we're talking about. What does that mean in the context of our field variables? Well, remember, we have 1 degree of freedom per point in space. Okay. So we should really replace this by some phi of x. And that index I is being replaced by some spatial position index x. So I really need to think about the commutator between phi at some point x and pi at another point y. And that should be equal to I times h bar, which is set equal to 1 because we're all adults here, times the delta ij. Okay. So what does that delta ij mean? Remember, we're taking the limit where all of these lattice points become very closely spaced together. And so that should become a delta function. And it should be a three-dimensional delta function that sets x equals to y. And this is the canonical commutation relation of quantum field theory. It plays the same role in quantum field theory that the commutator of x and p, being I h bar, does in quantum mechanics. And just as q with q commutes with itself, phi with phi will commute with itself, and pi with pi will commute with itself. So for example, phi of x and with phi of y will be equal to 0, as will pi of x with pi of y. I should make one comment here, which can lead to some confusion, okay? So I just want to dwell on it for a second. So the comment that I'll make is that when we talk about quantum mechanics, we often distinguish between what's called Schrodinger picture and Heisenberg picture. Okay? You guys probably have seen this in your quantum mechanics classes. So in Schrodinger picture, you think of operators that are independent of time. So the operators Q and P are independent of time. And when I write down these equations here, that's the sort of language that I'm using. Okay. Later on in this course, in fact, for almost all of this course, we'll be using the Heisenberg picture, where the operators depend on time. So in the Schrodinger picture, operators are independent of time, but you have the state that depends on time. In the Heisenberg picture, you just shuffle things around a little bit so that you have a state that's time independent, but you have operators that depend on time. So here, just to keep life simple, and because most people are most familiar with the Schrodinger picture, I'm using the language of the Schrodinger picture, where you have 1 degree of freedom per point in space, which is why I've labeled phi, pi, and phi by spatial positions, x vectors, without including a time there. But if we wanted to write everything in a way where space and time are treated more democratically, then we're going to want to use the Heisenberg picture where everything here depends on time. Okay? The equations will look almost identical when we rewrite everything here in Heisenberg picture, but I just want to bring that up because it is sometimes a cause for confusion. So right now, we're using Heisenberg, Schrodinger picture. You guys are all familiar with that distinction between Heisenberg and Schrodinger picture? Yes?
What are the states here? Just the field.
Well, I haven't told you what the states are yet, right? Because in the Schrodinger picture, what are the states? Well, the phi's, remember this phi is not a wave function. Phi is a classical degree of freedom. So the actual state is some wave function, okay? That's a function of your classical dynamical variables, okay? In quantum mechanics of a single degree of freedom, you'd write psi of x or psi of q. Here, you should write not a wave function, but a wave functional, okay? That would be a function of phi of x. And if you wanted to, you could develop the entire subject of quantum field theory in terms of the Schrodinger wave functional of quantum field theory. That is not the approach that anybody uses because it's much more cumbersome compared to the approach that I'm going to use in the Heisenberg picture. One of the reasons why it's very cumbersome is that you can see that in the Schrodinger picture, you don't treat time and space in the same way. You know, you think of space as a label for your operators, but not time. It's much more simple if you think of both space and time as labeling your operators. Okay. Right? In the Schrodinger picture, operators are labeled by space, but the states depend on time. It's much easier if you think of your operators as just labeled by space and time. Okay. Right, so I should really put in the Schrodinger picture psi of x and t. Okay. Indeed, just for fun, okay, let me tell you that you can think about the free scalar field in the Schrodinger picture. Okay. And in fact, you can solve the Schrodinger equation, the analog of the time-independent Schrodinger equation, to find the ground state of free scalar field theory. It's now a Schrodinger equation that's not, so the Schrodinger equation is Hamiltonian acting on psi psi is equal to 0. Okay. But now, usually the Hamiltonian, P gets promoted to a derivative d by dq when you write the time-independent Schrodinger equation. Now that's going to become a variational derivative d by d5 x. Okay. So the Schrodinger equation for the wave functional in this way of thinking about quantum field theory is not a usual differential equation, but is rather some variational equation for psi. In the same way that the Euler-Lagrange equation is a variational equation for the action. And you can solve that equation. Now that I think about it, that would be a really great problem set. But so let me mull that over. Okay, good. Excellent question. Other questions? Okay. Don't worry, we're not going to write down the Schrodinger wave functional of quantum field theory, as tempted as I am. Okay. So let me make another comment. Okay. So we're talking about a real scalar field, which means that as a classical variable, phi is just a real number, which means that, and moreover, it is an observable, right? The classical degrees of freedoms are the observables in quantum mechanics, which means that it should be, when you think about it as a quantum mechanical operator, it should be a Hermitian operator. So what I want to do now is really begin the construction of the Hilbert space of free quantum field theory, where I describe the Hilbert space that phi acts on as an operator so that it realizes the fundamental commutation relations. Let me see if there are any questions before I continue. So before I do that, it's going to turn out, of course, that the quantization of a free scalar field theory is going to be very simple, and it's going to reduce to a system that you all know and love. And in order to see why that is, let me just remind you of something that we discussed last class, which were the classical solutions of free scalar field theory. So the free scalar equation of motion, otherwise known as the Klein-Gordon equation. So the solutions to the equations of motion were easiest to think about if instead of talking about the field phi of x, we did a Fourier transform. So in particular, I'll think about the Fourier transformed field. So I'll write that as the integral d3p of e to the I p dot x times phi of p and t. Okay. So I haven't done anything here. All I've done is written phi in terms of its Fourier transform, okay, which I've called phi of p. Sometimes if you have a function of x and you take its Fourier transform, you call that, you put a tilde on top of it to remind yourselves that you have a Fourier transform. I'm not going to bother doing that here. I'm just going to use the notation where if it depends on p, it's in momentum space, it's the Fourier transform variable. If it depends on x, it's not the Fourier, it's the usual variable that depends on space. So the Klein-Gordon equation takes a very simple form in momentum space. So what was the Klein-Gordon equation? It said that dt squared minus the gradient minus grad squared plus m squared acting on phi is equal to 0. So if you stare at that, you can see what it means for the Fourier transformed field. It means that dt squared plus p squared plus m squared of the Fourier transformed variable is equal to 0. In Fourier space, the derivative with respect to x just brings down a factor of p. Okay. You can see that very explicitly. Just take this differential operator here and act it on this guy up here, and all it does is this gradient here, it only hits that guy and it brings down a factor of ip, brings down two of them, which gives you a minus sign, which turned that minus there into that plus there. Now, this is an equation which even I can solve. The solutions are, so phi will oscillate, and it will look like e to the plus or minus I omega t, where omega is the frequency that we discovered last class. It's the square root of p squared plus m squared. In other words, this equation of motion is the equation of motion of a simple harmonic oscillator. And so we see that this field phi is really just, can essentially be reduced to a simple harmonic oscillator. But it's not just one harmonic oscillator. It's an infinite number of harmonic oscillators, one for each momentum mode p. So field theory, or I should say free field theory, is one oscillator per momentum mode, and the frequency of the oscillator is omega p. There's a saying by a very well-known physicist, which is that physics is that subset of human experience that can be reduced to coupled harmonic oscillators. So this is definitely an example of that theorem, that statement. Good. Question? Yes?
You got harmonic oscillator, momentum, very slow.
No, we've got, remember, I've Fourier transformed, so you can either think of the field as a function of space or as a function of momentum. And if you think in Fourier space, you get one oscillator per momentum mode, right? I mean, if you think about the Debye model, which you worked out on your problem set, this is exactly what you worked out or will work out by tomorrow. Okay? In terms of your mechanical model, how do you think about it? Well, if you think about a bunch of balls on springs, well, you just what are these harmonic oscillators? They're just the different waves propagating on this lattice of balls attached to springs. And there's, for each possible wave number, that is, for each possible momentum, you have a different wave. And in the approximation where we're looking, where the Hamiltonian and Lagrangian are only quadratic in the field, this is just a bunch of free simple harmonic oscillators. Now, of course, in the lattice model where you have balls on springs, you don't have all possible allowed values of the momentum p. P will be quantized because you have a lattice model. But in the limit where the lattice sites are very close together, that everything will become very, very tightly spaced, and you'll essentially have one degree of freedom, or one sort of wave for every possible momentum. Good. Any questions on that? Okay. All right. Okay. So now let's think about the quantum theory. We saw that life got very simple if we, in the classical field theory, if we worked in momentum space rather than position space. Okay. So now let's do this in the quantum theory. So here phi is now not a classical field, but rather an operator. Okay. And we want to Fourier transform that operator. So we want to think of it as the integral d3p of e to the ipx times some other operator. Okay. And in fact, I'm going to introduce a normalization factor that's going to make our life simple. At this point, it's just a definition of the operator that I'm going to write down. So I'm going to write this as e to the ip dot x times an operator that I'll call ap. So hopefully the fact that I'm calling it a will get your minds thinking about something. Now, what I'm not going to assume is that A is a Hermitian operator, but phi is a Hermitian operator. So that means that in order for phi to be Hermitian, I need to add the Hermitian conjugate here. So I have to add e to the minus I p dot x times a p dagger. So right now, this is just a definition of this operator that I've called A. It's just the Fourier transform of the operator phi. The only difference is that I've relaxed the assumption that I'm allowing A to be a non-Hermitian operator. I could actually rewrite this a little bit, and I'm going to do that right now. So I'm going to write this as 1 over the square root of 2 omega p times e to the ip dot x, ap plus a dagger minus p. Okay. All I've done here is that in the second expression, I've done a change of variables where I've taken p to minus p. So that's just the same formula that I've written there. Okay, now I also am going to need to think about my momentum pi. Now, in order to understand what sort of formula I should write down for my momentum pi, actually let's just stare at this formula up here for phi. So what is pi? Given that solution, given those two solutions that I wrote down for phi, what is pi? Well, pi is the time derivative of phi, right? So pi will be plus or minus omega p times e to the I omega p t times I. So that motivates something that for right now is just going to be a definition. So I'm going to include a factor of I times omega p in my definition of pi relative to that of phi. Okay. So I'll write it as e to the I p dot x times ap dagger minus ap minus e to the minus I p dot x times a p dagger. So let me make one very important comment here. At this point, these two formulas that I've written down are just the definition of A and A dagger. So I started out with fields phi and pi, which were both Hermitian, and I've replaced them by a field A and another field A dagger. So hopefully you remember the simple harmonic oscillator. where one does something very similar. You write the field variable x as a plus a dagger, and you write p as a minus a dagger. And that's essentially all that I'm doing here. I haven't done anything here. So far, this is just the definition of what I mean by the operators a and a dagger. If you wanted to, you could invert these expressions that I've written here and write a and a dagger as functions of phi and pi. So all I've done is a Fourier transform to write these in a simpler form. Okay, actually, there's a minus sign, it turns out. That's just a definition. All these 2 pi's and omegas and stuff, right now, all that is a sort of convenient normalization factor for these operators A. Okay? And just as I did before, I could rewrite this as an integral d3p over 2 pi cubed times the square root of omega p over 2 e to the ip dot x times ap minus a minus p dagger. Good. All right. So what do we want to do? What we want to do is understand how to impose the canonical commutation relations. So in particular, what we want to do is study the commutation relation which says that the commutator of phi of x with pi of y should be equal to I times the delta function that sets x equal to y. So let's just go ahead and plug in our expressions here and see what we get. Okay. So in particular, I'm going to use these forms of the expression down here at the bottom because they'll make life a little simpler. So what do you get? Well, let's just write it all out. So first you get a minus I over 2. That's just from that minus I and these square roots of 2. You get an integral d3p from the Fourier expansion of phi and an integral d3p prime from the Fourier expansion of pi, where here now p prime is the Fourier mode for pi. You get a square root of omega p prime over omega p. And you get an e to the I p dot x plus p prime dot y. All of that times some harmonic oscillators. I spoiled the surprise. All of that times some oscillator, some of these modes, these operators, AP and AP dagger. So let's write that out. Well, first you have the commutator between this guy and this guy. Okay, that's 0. Any operator will commute with itself. You have minus times the commutator of this guy with this guy. So that's AP with A dagger minus P. Then you have the commutator of this guy with this guy. Okay, that's 0 again because A dagger commutes with itself. And then you have the commutator of this guy with this guy. So that's plus the commutator of A minus P dagger A P. Okay. All right. Now, of course, we could rearrange this a little bit and write this as minus 2. So we could write that as minus 2 times the commutator of AP with A minus P dagger. Okay. So you see that the commutation relation of phi with pi is very simply related to the commutation relation of A with A dagger. So, motivated by the fact that P prime, I'm sorry about that. Thank you. Okay. Yeah. Sorry. I was skipping ahead of myself. I can't make that simplification quite yet. So these are all p primes, thank you. So what do we get? We have a p prime there and a p prime there. Okay. So I can't make that simplification quite yet. Okay. Good, good. Thank you for doing that. Any other mistakes?
You also made the choice right away to say that the commutator of AP with AP prime is 0.
Oh, I did, didn't I? Okay. Sorry, I'm skipping a few steps. Yeah. Okay. Good. So there's a commutator. God, this is what happens when you prepare your lectures too late at night. You get an AP and an AP. You get two terms that look like that. Okay. Good. Thanks. Sorry about that. So let's just make a guess. Okay. You guys are paying attention. That's good. So the guess that I'm going to make is that AP with AP prime dagger is just equal to, oh, I also forgot my various 2 pi's. Okay. Is just equal to a delta function that sets P equal to P prime. And that, of course, as you've already anticipated, this AP with AP is equal to 0. So you can so that sets these terms equal to 0 here. And it says that this now is going to be a delta function that sets P plus P prime equals to 0. So I can use that delta function to do, say, the P prime integral, and it sets minus P prime equal to P. And then I can do the other P integral, and I can use the fact that the integral d3P of e to the I P dot x minus y is, up to some numerical constant, just the delta function that sets x equals to y. You guys have seen that before? More or less? This is the statement that the Fourier transform of a phase is a delta function. So if you haven't seen that before, well, if you haven't seen that before, I'm already over time, so I'm not going to explain it, but it's a true statement. It's just the statement that, well, it's just true. I mean, you use it all the time in electromagnetism. It's the statement that the Fourier transform of a delta function is a plane wave. In quantum mechanics, it's the statement that position space eigenstates are plane waves in momentum space. And momentum space eigenstates are plane waves in position space. So if you then use that, so we use the fact that one of these delta functions allows us to do the P prime integral. Then we can do the P integral. We have 2 factors of 2 pi cubed here. P prime is now, P prime is equal to minus P. Okay, so these 2 factors here cancel with one another. There was a factor of 2 that comes when you add up these 2 terms, which cancels that factor of 2. There was also an overall minus sign here, cancels that minus sign. And indeed, with this commutation relation, we find that pi and phi obey the correct canonical commutation relation. Okay. So I'm out of time here, but let me just step back so that we can think a little bit about what this means. So the conclusion is that we can always rewrite the degrees of freedom of a free scalar field theory as an infinite number of raising and lowering operators AP and AP dagger. Okay. So what I haven't done yet is computed the Hamiltonian of the theory. So as you can probably anticipate, given the fact that classically the theory looks like a bunch of harmonic oscillators, quantum mechanically what we'll find, and this is the first thing we'll see next time, is that the Hamiltonian is just going to be the sum of a bunch of simple harmonic oscillator Hamiltonians written as a function of the APs and AP daggers. Okay. So there was a reason why I had you spend hours and hours mucking around with harmonic oscillators on the problem set. Because free quantum field theory is nothing more or less than a bunch of uncoupled harmonic oscillators. Now, maybe I can just sort of whet your appetite for what we're going to discuss next week. So for a harmonic oscillator, if I hand you a harmonic oscillator, you can write the vacuum state, the ground state as a Gaussian wave function, and then you can use these ladder operators, these raising and lowering operators, to create states with 1 excitation, 2 excitations, 3 excitations, and so forth. When we quantize the scalar field, we see we now have these raising and lowering operators, 1 for each momentum mode. So what is the physical interpretation of these oscillators? Well, AP dagger is the operator that creates a particle with momentum p. And AP is the operator that removes a particle with momentum p. And so when you describe the Hilbert space of this theory, it's just a bunch of copies of the single harmonic oscillator Hilbert space, 1 for each momentum mode p. So there's nothing particularly fancy going on here. Okay. But it is a little bit of notation that one does have to get used to. Okay. So for that reason, next class we're going to spend some time manipulating more formulas of this sort to compute the Hamiltonian, and then I'll move on to compute the observables of the theory, namely correlation functions. All right. See you next Tuesday. Thank you.